Welcome to lesson 6 and the final lesson of year 2 pure mathematics sequences and series. Today we are going to look at something rather interesting. We're going to look at recurrence relations, and we're going to go very quickly into exam style questions on this. We're also going to look at how to classify sequences. So whether sequences are increasing, decreasing, periodic, or something else. All right, I've just defined two sets of numbers here. The natural numbers, which we use to define which term we're in a geometric or arithmetic sequence, or any sequence for that matter. And we've also got Z plus, which I don't think I've mentioned before. This is the set of positive integers, which you'll notice coincides with the set of natural numbers. So they are one and the same set, in other words, where we disregard 0 and we disregard all the negative integers. Okay, let's get started. Please pause the video and can you try the 4 warm-up questions, please? Great. Okay, let's have a look at the solutions. Okay, so question 1, I've just written up the next 3 terms of the sequence that you're given. Let's just go through the process. It's a sequence AN. We're taking n from the positive integers, in other words, the natural numbers. You might just want to just make a note of that, just to say that this is the same thing, what we're talking about here, the natural numbers. We have A1 as 1 and A2 as 1. And our first instruction is to add them together to generate A3, which is the third term of the sequence. And the way to do that is we seem to be adding the previous 2 terms, okay, which would be 1 plus 1, which we can see, which equals 2. And then for the next step, to generate A4, we take the 2 previous terms, A2 and A3. Okay, A2 is, of course, here, and A3 we've just found. So we add them together to get 3. So that's going to be A4. And then A5, we add the 2 previous terms, which are A3 and A4. So A3, we found earlier, it's here again. I'm just going to go over that again. So that's A3. A4 is the next one. So 2 plus 3, and then we get A5. Now you'll notice the pattern. Notice that the subscript for the sequence term is 3, 4, 5. It's increasing by 1 each time as we're generating more and more terms of the series, or sequence, I should say. So we're going to have 6, 7, 8 to continue that. And then in the first column on the right-hand side of the equal sign, each term is going up 1 each time, starting at 1. So 1, 2, 3, so that must go to 4, 5, and 6. And then the same pattern here, 2, 3, 4, will produce 5, 6, and 7. And then when we've located each of these terms, we simply add them together. So your next 3 terms are going to be 8, 13, and 21. And this may remind you of a famous sequence which exists in nature. It's the Fibonacci sequence. And you don't have to start with 1 and 1. You can start a Fibonacci sequence using any starting point, really. Okay. So that's that. So it's just generating more terms using previous terms. That's the key idea today. Moving on to question 2, we're asked to write an improper fraction that we're given here, 33 over 5. Notice it's top heavy, so it's improper, basically as a mixed number. And then once we've done that, we can express the numerator as the product of the quotient, which is 6, the divisor, which is 5, and then you'll get a remainder of 3. So the first thing to do here is to look at the 23 over 4 and just think to yourself, how many times does 4 divide into 23? Well, we know 4 times 5 is 20, so it's 5 whole ones, and the remainder is going to be 3, and the divisor is 4. Okay, and we'll do part 2 quickly as well. Again, 5 times 8 is 40. That will give me a remainder of 1, so it's 5 and 1 over 8. And let's write it in the form that's required. So for part 1, 23 in this case would be your quotient 5 multiplied by your divisor 4 and then you add 3. And remember, this is the same process whereby you convert a mixed number into an improper fraction. It's the same thought process. And on, sorry, not on the right, well, on the right, which is part 2, we'll just do that here. 41 is equal to 5, which is our quotient, which is the large number of your mixed number, multiplied by 8, and then adding 1. It may just be worth to just jot down what each of these numbers mean. So this is your quotient. That's how the whole number part when you divide by your divisor, which is incidentally the next number. So this is your divisor here. And unless the numerator is, of course, divisible by your divisor, you'll produce a remainder. So this is your remainder here. All right. So you'll see why that's applicable shortly. Let's have a look at question 3 now. So question 3 is rather interesting. We have to find the sum of the first 100 terms, okay, of the following series. Now notice that these are not typical arithmetic series. We can deduce the pattern visually, but they don't have a consistent common difference. There's different ways to think about this. What I'm going to do, I'm just going to show you one technique. You might have your own technique for doing this, but we'll talk about it maybe perhaps in a few minutes. So if you look at the first example, A, this series repeats every 2 terms. So I'm just going to partition the series into groups of 2. Now, if you'll notice, if I'm doing that, then I've got 100 terms that I've got to sum over. But if I partition them into 2, I can actually combine those into groups of 3, okay? And they're going to be half as many. So this is, of course, worth 3, okay? And rather than being 100, we're now going to drop down to 50 terms, okay? So we've actually got 50 lots of 3. Now, the 3, of course, is the same. You could think of that as an arithmetic series, okay, where you're adding 3 each time. But also, it's just going to be, it's multiplication, isn't it? It's the additive side of multiplication. So for part A, we can write it like this. So A is just going to be 50 multiplied by 3, which is 150. Okay, now that's one way to do it. Second way to do it, I'm just going to show you just an alternative, if that's okay. So alternative depends on your thought process, doesn't it really? Notice we've got a pattern alternating between 1 and 2. What if I reorder this series? What if I say, okay, I'm going to put all the 1s together, and then I'm going to put all the 2s together. Like that. Now we can do that because we know how many there are of each. Okay, if there's 100 terms, and we know that we've got 2 different numbers, 100 is divisible by 2. That means that I must have 50 of these 1s, and I must have 50 of these 2s. Okay, so now it's quite simple. So I've got 50 1s is just 50, isn't it? Okay, so remember the sum of n terms of 1 is just n. And then 50 lots of 2, so I've got plus 50 multiplied by 2. Okay, and that's, of course, going to give me the 150 that we saw a moment ago. So that's just an alternative. Okay, now for part B, what we've got here is we've got a same alternating series. We've got 1, subtract 1, add 1, subtract 1 in that fashion. Now I can again partition them like so. So I'm just splitting it up into groups of 2. And once again, if I've had 100 terms initially, I can then just bring that down to 50 terms. So, and these are all going to be 0. And we've got 50 zeros. All right. So for the answer for B is obviously going to be just 0. Okay. Nothing more than that. I won't do the alternative, but obviously you could sum the 50 ones, which would be 50. And then you could sum the 50 negative ones, which would be negative 50. And you would have 50 subtract 50, which is, of course, 0. Now, moving on to part C, let's just have a look at the series itself. How could we do this? Well, I'm going to use this partition method again. And we've got 3 different or distinct terms to deal with here. Now, this is going to create a slight problem. If I've got 100 terms behaving in that fashion, then if I'm dividing by 3, that's going to give me 33 of these groups, but I'm also going to have a remainder of 1. Okay, now that's important because that means that on the 33rd, excuse me, the 33rd group is obviously going to end in a 3. But once I've added them together, of course, it's just going to be 6. But I'm still going to have that extra 1. So what I mean by that is if we just consider the final few terms, I'm not articulating this well. If we look at the final few terms, so the 100th term is not going to be 3. So let's just think about this. Okay, so you've got, let's do this again. Getting a bit tongue-tied at the moment. So this is the final few terms. Now, if I divide, if I've got 100 terms and they're divisible by 3, the last term that is divisible by 3 is the 99. So that means that I know that the 3 here must be the 99th term. Okay? That makes sense, doesn't it? Because that's divisible by 3. This must be the 98th term, and this must be the 97th term. Okay. Now that means that the 100th term would be a 1. Okay, so we'll add that on. So that would be plus 1, and that would be the 100th term. Okay, so that means that my remainder here is this extra 1 here. Okay, I hope this is making sense. So let's just have a look at these groups. Well, each of these groups is just worth 6. Okay, and there's going to be 33 of them. So let's do the calculation now. So it's 33 multiplied by 6, 33 of those. And then that 100th term, I'm going to have to add it on. So we can calculate that, and that's going to give us 199. Okay, and you can obviously do that in many different ways. You could group together all the ones. There'd be 33 ones, there'd be 33 twos, and 33 threes, but then there'd be an extra 1 in the one group. So you could group them together like that. Okay, and then lastly, let's move on to question 4. I've just added the solutions here. I'm just going to talk through a few of them about whether these sequences are increasing or decreasing, and maybe we could write some of them out. So if we look at the first one, we have 0.1 to the power n plus 1. Now, if I just jot a few things down here, let me just create a bit of space over here. Just partition that off, and we can do try a few ideas out. If I have 0.1 to the power n plus 1, then I'm going to have 0.1 squared is my first term, 0.1 cubed, and so on and so on. And we know that when you square or cube or increase the power of a number between 0 and 1, it's obviously going to decrease, and you can check that in your calculator. So that's definitely decreasing. For B here, this is periodic, simply because the sine wave is periodic. It oscillates between -1 and 1. So taking sines of multiples of 90 is obviously going to create that, and you can see that from your sine graph. So I won't go into that one. Part C is very interesting. So for B, just put some numbers in and you'll see it. Multiples of 90. For part C, this is rather good. This is actually the definition of an increasing sequence where the new term is greater than the previous term. Okay, that's what that inequality means. So that's an increasing function. So beg your pardon, increasing sequence. D. Now, D, we might just need to have a little look at. What's going on here? Well, let's put some numbers in. Well, if we have 0.1 and I put in the first one, it's 1 subtract n is a natural number. So it's going to be 0.1 to the 0, which is, of course, just 1. And then my second term is going to be 0.1 to the power 1 subtract 2. Now, that's 0.1 to the power negative 1. Now, 0.1 is 1 over 10. Now, if I reciprocate that, which is what the negative 1 power does, this is just going to be 10. Okay, and this is going to keep going. So if I do 0.1 to the power negative 2, that's going to be 100. So it's increasing by a factor of 10 each time. So D here is certainly an increasing function, although it may not look it on first glance. Moving on to E, you probably won't be surprised to learn now that this is the definition of a decreasing function, where the latest term is less than the previous term. For F, I'm just going to create a bit of space. Let's have a look at F and see what's going on there. This looks a little bit complicated. So just to try and convince you of this, we have negative 0.1 to the power n plus 1. Now, notice it's just the negative version of A. Okay, so A we found was an decreasing function. So if you change the signs of all of the terms in sequence A, now that's obviously going to make it a increasing function, isn't it? Because very simply, if A was, let me just, for example, it was 0.1, no, it won't be, it will be 0.01. Let me just undo that. 0.01, 0.001, it would go like that, wouldn't it? Okay, now if you change the signs of those very quickly, you can see that's now increasing. It's getting closer and closer to 0, but never quite getting there. So it's increasing, but the gradient, if you like, you think of it as a continuous function, the gradient is getting closer and closer to 0. All right, so that's why F is increasing here. Now moving on to G. G is slightly different. Let's just do a bit of work on G. So G is, let's put some numbers in, negative 0.1 to the power n minus 1. So the first term is just going to be 0, so that's going to be equal to 1. Then we're going to have negative 0.1 to the power 2 subtract 1, which is 1. So it's going from positive to negative. And then the next term is going to be negative 0.1 squared, which is 0.01. Now, that's the reason why we have left G off our list. So the sequence, if you can imagine, as we go through each term, so there's term 1, there's term 2, there's term 3, if you like. The sequence starts at perhaps the value 1, like this, and then it goes down to negative 0.1, which might be there, and then it goes up to positive 0.01, and then it's going to go negative again, but get close to 0, positive again, but even close to 0. So it's actually oscillating. So this actually doesn't fit in any of these. You can't say it's periodic because it's changing size. There's no repeating values, okay, but they are oscillating between negative 1 and 1. So G is what I would term an oscillating sequence. Okay, now H. Now this is a very interesting one. H, this is periodic, similar to the sine sequence. Now, let me just explain what this means. Suppose, for example, my A1 in my sequence is equal to 3, okay? Now, that means that my A4 is also equal to 3, because, let me just explain this. Because if we have n as 1, n plus 3 is also the same. Now, I could define this sequence however I like now. So I could say, all right, if my A2 is equal to minus 1, it doesn't matter what it is, what's going to be the same? Well, if I add 3 to my 2 subscript there, that's going to be 5. So I also know my A5 is negative 1. And then I could do the same thing with A3. So my A3, let's say my A3 is 2. That means my A6 is also 2. Now look what's happened here. This is quite interesting. We've created the sequence, okay? So we've got 1, 2, 3, 4, 5, 6, and the sequence is periodic because it's going to go 3, negative 1, 2, and then it's going to repeat 3, negative 1, and 2. And it's going to do that over and over again. So it repeats every 3 terms. Okay, so I think that concludes the warm-up. So now we're going to look at the idea of a recurrence relation and how to write a recurrence relation first of all, and then we're going to move on to problem solving. So we'll get into exam territory pretty quickly with this. So we have 2 examples, and this is not usually a requirement, but I'd like you to sort of appreciate how to write a recurrence relation, because it really gets into the the fine detail of how these things are constructed. So let's have a look at this. We've got the first one. We have an arithmetic sequence. So it's an arithmetic sequence you know really well. So let's just have a look at what we know about it. Well, we know that to get from one term to the next, we're simply just going to add 3 in each case. So there's nothing wrong with that. And there's various things we can do with this. But what we've not done is we've not written this as a recurrence relation. And what is very common with recurrence relations is we start with the first term, and then we define the remaining relation based on that first term. So what I mean is, if we say U1 is equal to 4, and this is the first term, so I'll just make a note of that. Normally we would call this A, wouldn't we? All right, but we'll call it the first term U1 in this case. Now, how would I define the second term? Well, let's have a look what we know. The second term, we've already got it. We know that it's 7. Okay, but let's think how we got there. Well, we started with the first term, didn't we? And we added our common difference, which is 3. That's how we got to 7. So now I know it's 4 with 3 added. I could actually write it like this. I could write it as U1 with 3 added to it. Okay. So we've now defined the second term as 3 added to the previous term, essentially the first term. And let's see if we can continue this pattern. So if I look at the third term, which we know is 10, well, 10 is the same as the 7, which we had for U2, and we added 3 to that, didn't we? That's how arithmetic sequences work. So we could write this as the previous term U2 with 3 added. Now, notice what we've got here. We've got a pattern. We've started with U1 equals 4. Now that was given to us. We have to have a starting point, otherwise there are an infinite number of possibilities of creating sequences where you add 3. Now for U2, we stated U2, and once we'd broken it down, we had it as U1 plus 3, and then we created U3 by adding 3 to U2. So how could we generalize this? Well, it's actually quite simple. So if we just sort of continue the idea, so if I want to create a new term, let's call it UN plus 1. It's exactly the same as taking the previous term, UN, and adding 3 to it. Okay, so what we do is we define our recurrence relation in the following way. We say, okay, the first term is 4, U1, and then to generate the rest of the terms, we use this rule. Okay, so this is our recurrence relation for this arithmetic sequence. And you can see that the first term and the common difference are still present. First term is 4 and the common difference is 3. So it still uses those key ingredients. And now we're going to move over to question 2, example 2, I mean. What have we got here? Well, we've got a geometric sequence. So maybe just pause the video and see if you can do this yourselves, and then we'll go through it. Okay, well, let's have a look at the common ratio. After all, this is a geometric sequence. So to get from 2 to -6, I've multiplied by -3. And similarly, to get from -6 to 18 and from 18 to -54. So we know our common ratio, and we also know our first term. So in the same way, let's write down our first term, U1, which is equal to 2. And what was our second term, and how does it relate to the first? Well, if U2 we know is -6. All right, now if we take our first term, well, we multiplied that by -3, didn't we? So I can simply write this as -3 multiplied by U1. So now you can see, because this is geometric, it's a multiplicative relationship. We're not adding 3. We are multiplying by -3. U3, let's just do one more. So we know that is 18. And this is the previous term, which was -6, multiplied by -3. So in other words, it's -3 multiplied by U2. And we can continue in the same fashion. So what would our general term be? Well, to get the next term, you would take the previous term and multiply it by -3. So in this instance, we can define our recurrence relation in the following way. So our first term, our starting point is 2, U1. And to generate the rest of the terms of the sequence, we simply multiply them by -3, the previous term. Okay, so that's just how to construct a recurrence relation. And now we'll move on to solving problems. Now, in these worked examples, you'll notice the good thing about recurrence relations is you don't need to know an awful lot about sequences because you're just given the instructions to follow, and you can generate whatever sequence is given to you. So in this instance, we're given U1 is equal to 3. That's our starting point. They have to give you this information, otherwise you wouldn't have no idea how to start your sequence, because there's nothing for your recurrence relation to take purchase on. So you're going to have to they're going to have to provide that. Now, how do we generate the next terms? Well, notice that we've got these subscripts n plus 1 and n, which we saw previously. Now, a good thing to do is just to substitute n equals 1, n equals 2. These are natural numbers into the recurrence relation just to see what's going on. So let's do that first. So when n is 1, our recurrence relation, well, that would give us U2, wouldn't it? Because n plus 1, if n is 1, that's 1 plus 1, which is 2. So u2 is going to equal u1 squared plus 1. Yeah? Similarly, before we substitute anything in, when n equals 2, we know that u3 this time, which is 2 plus 1, so that's n plus 1, is equal to u2 squared plus 1. Okay, and then we're going to need the first 4 terms. So when n equals 3, we've got term 1 was given to us, wasn't it? That will give us u4. So that would be u4, that would be u3 squared plus 1. So that's just subbing in the values of n, 1, 2, 3, the natural numbers. And then you can see the pattern emerging here. All right, so let's look at u2. Well, we have to take the previous term, u1, which was 3. So we're going to sub that into the next term, aren't we? So that's going to give us the following. So that's going to be 3 squared, and then we're going to add 1 to that. So that's just going to be 10. Okay, and we've got our second term. Now we've got our second term, we can find the third term because it relies on the second term. So this second term is now going to be fed back in to our expression here. Okay, so this is going to be 10 squared, and then we're going to add 1. So this is going to be 101. Okay, and now we've found u3. We need one more term, so we're going to take this 101 and we're going to feed that back into our recurrence relation here to get the next term. Okay, so it's just a nice pattern. So this is going to give us 101 squared with 1 added. Okay, and that is 10,202. Might just need your calculator for that one, but there you go. So those are the first 4 terms of the sequence. So just to write them out explicitly, our sequence starts with 3, then 10, 101, and 10,202. And then there will be more to come, but those are the first 4 terms of the sequence. So now we've had a look at a straightforward example. I don't think there's any danger in. We're gonna go into the exam territory now. We can solve problems with this because the basic idea doesn't change, as is the case with a lot of the maths that you've learned. Okay, it's just applying it to problem solving where maybe the problem is asked in reverse or there are certain unknowns we need to deal with. So in this instance, we have a sequence. They can be defined in many different ways. So A1, A2, A3, etc. You can have U1, U2, as we've just seen. It doesn't really matter. They will define that for you in the question. And as I said before, they're going to provide you with the first term or one of the terms if it's a problem-solving question, and then you can reverse engineer to find the first term. And you also need the relation. So how do you generate all the rest of the terms from that first term? So at the moment, it looks quite complicated when it's written in that form. So let's unpack this and let's see what happens when we start subbing in the natural numbers. So for part A, I'm going to use this space here. You've got space to write below, but feel free to use this space here as well. So for part A, I just want to substitute in n equals 1 into this recurrence relation. Okay, and we'll see what happens. So this is going to generate A2. Okay, so 1 plus 1 is 2. And we know that A2 is going to be A1 according to this. And then we've got a bracket. So we have this unknown constant P, which we know is non-zero. That's all we know about it. And we add the previous term A1 to that according to this relation. Okay, that's fine. Now, let's actually start to substitute in, because we do know what the first term is. It's here. A1 equals 1. So I just sub this into what I've just written down. And that means that my first part, the first factor, that A1 is going to be 1. And then I'm multiplying the 1 by P added to A1, which again is 1. So the 1 appears again. So that's just 1 multiplied by the linear expression P plus 1. So it's just going to be P plus 1. Now let's highlight that, make it look really clear. So we've now found A2, just through a little bit of work. And A2 we now know is P plus 1. So as you can see, this is problem solving. We don't have an explicit value. We've got it as a linear expression. And we'll have to find P later on. Okay, let's just carry on with that. So let's substitute in the next natural number. So n equals 2. Now that's going to generate A3 for us, isn't it? Okay, so I've done part A. I've found A2 in terms of P. That's just P plus 1. So I'm now on to part B. Okay, so it doesn't have to be a whole load of work. So A3, so it's going to be the previous term. So that's going to be A2. And then it's going to be P added to the previous term again in the bracket. I'm putting them next to each other. I'm hoping you can see the pattern here, and you could probably just write down as many of these as you like now, if it was necessary. So now we're substituting our previous term. Now our previous term we have just found is here. So the P plus 1 is going to have to go back in to this, as we saw in the previous example. So now we've got P plus 1. And because that's a linear expression, I'm going to have to put that in brackets, because it's going to multiply the expression next to it, which is P added to the P plus 1 again. We're going to substitute the A2 in again. So that's P plus 1 there. And then we close that bracket. Now we're just going to tidy this up a little bit. So this is going to be P plus 1 multiplied by, just collect like terms, 2P plus 1. Okay. And notice the question is asking us to write it in this form. So I'm going to have to expand this bracket. So let's do that. Just a quadratic, isn't it? So we're going to have 2P squared plus P plus 2P plus 1. And that looks correct, doesn't it? I'll write it in the normal way. So it's going to be 2P squared. When I say normal way, I mean in descending powers of P. Added to 3P, added to 1. So I know that's correct. It's just written backwards. Okay, good. Right, okay, for part C, we have to find this value of P, and they've given us some extra information. They've told us here that A3 is equal to 1. Okay, that's good. So I can just set, remember this is A3 that we found here. All right, so if I just set this quadratic equal to 1, I should be able to answer this question. So for part C, we'll set 2P squared, add 3P, add 1, equal to 1. So the 1s will cancel. So therefore, 2P squared added to 3P must equal 0. I'll just move across over here. So that implies, if we just factorize it, that P, which is the only factor I can take out, multiplied by 2P plus 3 must equal 0. So if we just solve this blindly, okay, this means that P equals 0, or P is equal to -3 over 2. Okay, those are my two solutions there. Now, I said we're just solving this blindly. We need to be careful here and go back to the context of the question. It says P is a non-zero constant. And it also says find the value of P, implying that there's only one value to find. That means that I can disregard this value here. Okay, this can't be true because P has to be non-zero. So the only value of P I need to worry about is this -3/2. Okay, so that's good news. And now we're going to look at this sum here. Now this sum, it looks really complicated. Okay, but if we think about it carefully, we should be able to solve it pretty quickly. In fact, it tells us to write it down, and that's a huge clue here because this should not be a lot of work, all right, if we're smart about it. So let's go back to the sequence and let's see if we can generate a few terms of this sequence so we can see what's going on. So this is for part D, which I'm going to do this down in the bottom left for the moment because we've got a bit of space here. So the sequence, the first term is, of course, just 1. Okay, we were given that. Now, remember the second term, A2, that was P plus 1, wasn't it? But we now have this value of P. We've just figured it out. So P plus 1, that would just be -3/2 plus 1, which is, of course, -1/2. All right. So we now have the second term. We've also got the bonus that they told us in the question that A3 is just 1. So we've gone back to 1 again. So what's actually going on here? If A3 equals 1, how does that work? Well, we could find out what the next term is. Now, rather than using this awful quadratic expression here, if we go back to the original recurrence relation up here, we know, and I'll just do this as in a different color, just as an aside here, the A4 term would simply be A3, the previous term, and then P plus A3 inside the bracket. And remember, we know what A3 is, and we also know what P is. So I can write this down really quickly. If A3 is 1, so that's just going to be 1, and then P is -3/2. All right, and then I'm adding the previous term again, A3, so that's plus 1. I've essentially just got the -1/2 again. Okay. And you can keep going with this. If you do A5, you're just repeating a step that you've done previously because you're going to be using A4, which is -1/2. Okay, and then you'll just generate the term 1. So we have what we call a periodic sequence here. So the sequence behaves like this. So it's going to just be, in fact, I'll write it as the series. We'll write this summation now we've figured out what's going on. So it's going to be 1, subtract 1/2, and then add 1, subtract 1/2, add 1, subtract 1/2, and so on and so on. Okay, just from these results here. If you can test it yourself, feel free to do that. But we have 1, -1/2, 1, -1/2, and you'll see once you've done a few of these that it's just going to keep doing that because you're just regurgitating the same steps. Now, we've seen an example like this in the starter. We dealt with this earlier. So this is going to be summed over 100 terms. Now, it's completely up to you how you do this. I'm going to combine them. So I'm going to put them in groups of 2. So this is going to be 1 subtract 1/2 plus 1 subtract 1/2 plus 1 subtract 1/2. And if I group them in groups of 2, that's going to halve the number of terms I'm going to have to sum. So this summation is just going to be 1/2 plus 1/2 plus 1/2 plus, and so on and so on. And then because I've essentially divided my 100 terms into groups of 2, I'm just going to have 50 terms of a half. And that's really straightforward. So I can just say, right, well, this is just going to be a half, but 50 times. So the sum would be 25. Okay. Now, I did stress that it does say over here, write down the value. And I know I've not just written down the value, but if you're confident, just go right ahead with that. I would just recommend, though, writing out a few terms of the series, see what's going on, and use this nice technique here where you can group them and just use a bit of common sense. All right. Okay. And we'll move on to example 3. So this is another quite interesting problem here. We have U1 as 4/5, and UN plus 1 is the reciprocal of it. Now, you're going to see something quite interesting here, and it just falls out really nicely and really quickly. So let's just write out a few terms of this recurrence relation. So U1 is given to us. I'm just going to state it again. So this is all going to give us the answer to part A. So if U1 equals 4/5, that's my starting point. And if I use the recurrence relation, my second term, U2, is going to be 1/U1. Okay, using the previous term. And because we know what U1 is, it's going to be 1/4. So it's the reciprocal of that. And we can write this, as you know, if you multiply top and bottom by 5 to clear the fraction, the reciprocal is just going to flip it over. So we're going to get 5/4. So we now have the first 2 terms. It's not really enough, is it? We need to do a bit more work here, but you can probably see what's going to happen. If I do U3, we're going to have 1/U2. And this is going to be 1/, the previous term, which we've just found, which is 5/4. Remember, this gets fed back into this. So we put 5/4 there. And then it just undoes. It's an inverse operation, isn't it? It just undoes what we've done previously. So this is going to give us 4/5. Now, I think we can confidently say, without doing any more work, this is just going to keep going on. So the sequence is going to run like this. So we'll talk about the period in a minute. Sequence is going to run 4/5, 5/4, 4/5, 5/4, and so on and so on, without end. Now, the question asks us for the period. You can probably guess what this means. This is a periodic sequence in the same way as the sine of 90 degrees multiplied by n was in the starter activity, which you had to classify as periodic. The period is just how often does this repeat? Well, it repeats every 2 terms. Okay, so once you've done the first 2 terms, it's just going to repeat again. So that you can group them into pairs of 2. Okay, and then it just repeats that pattern. So because there's 2 in there, we call this periodic. Okay, so it's periodic of order 2. Okay, so the order of is basically how many terms does it take before it repeats. Yeah. Now we've stated the period, we can now find this summation. Now the summation looks tricky in this instance because we're summing from 1 to 201 this time. Right, let's just write out what's going on. We've got the sequence generated, so let's see if we can see some nice patterns here. So we know this is going to be 4/5 added to 5/4 added to 4 over 5, added to 5 over 4, and so on and so on. Now, remember this is in groups of 2. So there's going to be 100 of these pairs, isn't there? 100 of those pairs. But that would only give us 200 terms, okay? So there'd be 100 of those pairs that I've just highlighted in yellow. This means that we're going to have an extra one. So the final term, so just to finish this off and hopefully give you a good indication. So it's going to carry on and on and on. So 4 over 5 plus 5 over 4. Okay, now that, we'll call these the last pair, if you like. And then we're going to get this extra term where we get plus 4 over 5. Okay, so there's 100 pairs plus 4 over 5 because there's a remainder of 1. And you can do this if you simply just do 201 divided by 2, you get 100 remainder 1, don't you? The remainder 1 is, of course, the 4/5. So the remainder 1 here is this 4/5 here. Okay, I hope that makes sense. So that's just the thinking behind it. Now let's think how we can actually calculate this. So what we could do is we could add up these pairs and then multiply them by 100. What might be easy though in this instance is if we group them into like groups. So rather than having 100 groups of 2, we have 2 groups of 100. So what I mean is we sort out the 4/5. So it's going to be 4/5 plus 4/5 plus 4/5. So there's going to be 100 of those. And then we're going to have 100 lots of 5/4. All right, and let me just highlight that again. So this is, there's going to be 100 of these, and there's going to be 100 of these, and then not forgetting that we've got the extra 4/5 to deal with over here. Okay, now we're ready to calculate it. Now, obviously, when you're doing this, you don't have to do all this working out. This is just me explaining it to you, okay? So it's 4 over 5 multiplied by 50. No, beg your pardon, sorry, 100. There's 100 of them. And then we're going to add 5 over 4. And we'll multiply that by 100. Okay, and then we're going to add the 4/5. Okay, so this is going to be, so that's 400 over 5. Oh, I just wanted to undo that text. There we go. So it's 400 over 5. Plus 500 over 4 plus 4/5. So 80. And then 500 over 4. So that's half of 250. So that's 125 plus 4/5. So in other words, just to finish off, this is going to be 205 with and 4/5. Okay, so that's the sum. Okay, and I'm not saying you have to do it that way. It's just one way of thinking about it. So our final example, worked example 4, we're given basically an exam context. Okay, this is the kind of thing you'll be expected to do. So there's key properties in here that we need to be aware of. So we have this sequence A1, A2, A3, A4, etc. Given here. We've got our recurrence relation provided here. And we're also told that the sequence is periodic of order 3. Now then, oh, and K is also a constant. So there's some key information here we need to be aware of. So let's just consider this idea about the sequence being periodic of order 3. Now, just to explain this again, we touched on this earlier in a previous question. I'm just going to write it out. If we have a sequence, so A1, doesn't really matter what they are, A2, A3, A4, A5, A6, etc. Okay, if it's periodic of order 3, remember we saw a sequence that was periodic order 2. So there's 2 distinct terms in the sequence, then the pattern repeats. So what this means is, let's get the highlighter on it. These 3 terms would be distinct, okay? And then A4, A5, and A6 would be a repeat of A1, A2, and A3 in that order. Now we can explore this more generally. So what I'm saying in this instance is that A1 would be exactly the same as A4, okay? Because of this pattern, it's repeating every 3 terms. Okay, I suppose technically it's every 4 term, but there's 3 distinct terms that repeat. A2 is going to equal A5. A3 is going to equal A6, and so on and so on. Now, let's just generalize this. So if we just go ... what about the general form? Well, for a sequence that is periodic of order 3, we know that if we have AN, for example, the general term, it's exactly the same as AN plus 3. Okay, and you can see that all the way down. So if we have 1 there, okay, if you add 3 to 1, you get 4. You add 3 to 2, you get 5. And if you add 3 to 3, you get 6. So we have this general form. So this is one way we can define our periodic sequence. So it's really, really worth just making a big fuss over this. So I'm going to put that in a box because we need to remember this. That's what it means in a general case as well. Okay, so let's go back to our recurrence relation. We haven't been given a starting point yet, but in part A, they wait until part A until we get that. And then we have a show that question. So we have to show that we get this quadratic in terms of K. So let's start by writing down some of the terms of this sequence. So I'll start down here. So we know that A1 is equal to just 1. Okay, sorry, this is part A. We know that A2, using the recurrence relation, is equal to 2K divided by the previous term A1, and then with K subtracted. Okay, now we can sub in A1 now, can't we? Because we've been given that. So this is going to be subbed in here, so I can replace that with 1. All right, and let's do that. So we're going to have 2K over 1 subtract K, which is just 2K subtract K, which is just K. So we've now got our A2. It's very nice. It's very simple. So A2 here is just equal to K after a bit of work there. Right, let's continue with this. So let's find A3. So A3 is we're going to take 2K and then we're going to divide that by A2, the previous term, because that's what the recurrence relation tells us to do. So it's AN on the bottom there. Then we subtract K. So this is going to equal 2k over the k we've just found, which is here. So this needs to be fed back in. Let's do that. So it's 2k over k, subtract k. Now the k's will cancel here. So they're just going to cancel out. Okay, so we're just going to be left with 2 subtract k. All right, now we've got A3. So we'll just highlight what we've just found there. So these are important. So A3 is 2 subtract k. Now, let's think about this periodic order 3. In this instance, if it's periodic order 3, remember what we said earlier, the A1 term must equal A4 in this case. So whatever my A4 is now, I know it's going to be equal to 1, whatever I get. So let's write it out. So A4 is going to equal 2k divided by A3 subtract k, which is equal to 2k divided by 2 subtract k subtract k. And I could write that as a single fraction, but I'm going to leave it. Okay, I'm going to leave it like that. So what we found is A4. We've got an expression here for A4. Now, and I've just said that A4 must equal 1, whatever we get. So let's set up an equation now. So I'm going to take this. We'll do some work over here. So since A1 is equal to A4, because it's periodic of order 3, we can now say that 2k divided by 2 subtract k is equal to 1. Now, if we manipulate the algebra, hopefully we'll get a quadratic here. So let's multiply everything by 2 subtract k. In fact, what I will do, I'm going to add k to both sides first. So we're going to have 2k divided by 2 subtract k is equal to k plus 1. All right. Therefore, 2k is equal to 2 subtract k multiplied by k plus 1. Okay, I'm just running a little bit out of room here. I'm just going to move across. You've got a bit more room than me, so feel free to carry on down the page. Let's expand the brackets on the right-hand side. So we have 2k is equal to 2k plus 2 subtract k squared subtract k. Right, let's collect like terms. We'll do that on the left-hand side. So I'm going to add everything to the left-hand side now. So we're going to have k squared plus 2k subtract 2k subtract 2 plus k is equal to 0. And just to finish off, collect your like terms. So the 2k's will cancel, but we're going to have plus k subtract 2 is equal to 0. And there we have it. So we've just shown that we get this nice quadratic here. Okay, so that bit's done. Now moving on to part B, we have to find the sum. Now initially we've got this quadratic. It's a good idea. Let's solve this quadratic and find out what k actually is. So the quadratic we've just found factorizes rather nicely. So we're going to have k plus 2 multiplied by k subtract 1 is equal to 0. It factorizes really nicely. And if we solve that, we're going to have k is equal to -2 or k is equal to 1 as our two possibilities. Now, this means that if we have two possibilities for k, this means that we're generating two completely different sequences, or, well, perhaps that's what it seems to allude to. So what happens if we have k equals 1? Let's start with that one. So for k equals 1, what happens? Well, my first term A1 is still going to be 1. That's not going to change. Now, my second term that I found which is A2, was equal to K, if you remember from previously. So my A2 is just going to equal 1. Okay, and my A3, which would be the third term, that was 2 subtract K. So that would be 2 subtract 1, which is also 1. Okay, and then the A4, and you can check this yourself, it was 2K over 2 subtract K subtract K. Well, if you do that, you will have 2 over 1 subtract 1, which is 1. So I get 1 for all of the 4 terms so far, and it looks like the whole sequence is just going to be 1. Now, there is a caveat in the question. It does say that given that A1 does not equal A2, and clearly here A1 does equal A2. So this can't be right. So we're going to have to disregard this value of K. This is not going to give us the result we need. What we need to do is we need to consider what happens when K is equal to -2. So when K is equal to -2, we're going to have the following sequence. We're going to have A1 is equal to 1. A2 is equal to K, which is -2. A3 is equal to 2 subtract K, which is 2 subtract -2, which is 4. Okay, and we know because this is periodic of order 3, that A4, no matter what I get when I sub in the K value, I don't even have to think about that. Doesn't matter. I know it's going to be 1. So that's our sequence. Now, our job is to find this sum. The sum for the first 50 terms of our sequence. Okay, now I'm just going to create a bit of space and then we can have a go at this. So this series is going to be the sum of 1 subtract 2, add 4, plus 1 subtract 2, add 4, and so on and so on. Okay, and we're summing over 50 terms. So let's think of a strategy to do this. Okay, we have a periodic of order 3. That means it's repeating every 3 terms. So I can group these into groups of 3 like so. All right, now if I'm summing over 50 terms, now 50 is not divisible by 3. So if I just quickly do that, 50 divided by 3, as we know, is 16 remainder 2. I'm going to write it as remainder 2. So this is going to, you're going to have 16 groups of 3 plus 2 extra terms. All right, now just because we've done a couple of these, it's quite straightforward. So you're going to have 16 lots of this 1 subtract 2, add 4. Okay, there's 16 of those groups of 3, but then you're going to have to add 2 more terms. So we're going to have to add the 1 and then subtract the 2. Okay, so we just have to finish this calculation. So this is going to be 16 multiplied by 1 subtract 2, which is, of course, -1 plus 4, which is 3. And then we're going to add 1 and subtract 2 again. Well, that's the same as subtracting 1. So our final answer is going to be 16 times 3. So that's going to be 48. Subtract 1. So the sum is going to be 47. Okay. And that concludes the lesson and the entire topic.